Hi, and welcome back to another episode in the C# Practical Funkiness series. Today we're going to take a look at the state monad. Unlike some of the concepts that we've covered in earlier videos, this is something I haven't yet used myself in either production nor in personal projects. That said, I felt it was worth including in this series to round out our functional programming toolbox. I'll be honest, this one took me a while to get my head around. I'm so used to managing state through class level fields that I'm still figuring out exactly where I might apply this approach in practice. That said, if it's anything like my experience with partial application a few years ago, I'll probably end up wondering why I didn't start using it sooner. So what is the state monad? The state monad is a functional programming pattern that allows you to thread state through a sequence of computations in a clean and predictable way. Instead of relying on class fields and mutating shared state or explicitly passing state as a parameter to every method, the state monad extracts this process. It allows you to define functions that implicitly access and update the state, producing both a result and a new state at each step. This makes state transitions explicit, avoids hidden mutations, and helps you build complex stateful logic in a pure and composable way. Right, let's dive in and take a look at my implementation of the state monad. The first thing to note is that the state type has two type parameters. TState, this represents the type of the state being threaded through the computation. TValue is the result type of the computation. I say result of the computation because, as you'll see, nothing actually happens until we explicitly run the process. This deferred execution model is part of what makes the state monad both powerful and, in my case, initially a little tricky to grasp. Also, something that might catch your eye or even trip you up if you're looking for it is that there is no field that stores the state itself. The state monad doesn't contain a state. Instead, it wraps a function that knows how to take a state and return a new state and a result. On line 7 we have a private field named _run, which holds a function, and this is really the core of the state monad. It's a function that takes some state of type TState as input and returns a tuple containing two things: TValue, which is the result of the computation, and a new TState, which represents the updated state after the computation. This function is not executed immediately. Instead, it's stored and composed as we build up our monadic chain, and it only gets executed later when we explicitly call run. The constructor takes a delegate, or in practical terms, any lambda or method that matches the signature of our private field. That is, a function that takes a TState and returns a tuple of TValue and a new TState. This is how we wrap a computation inside the state monad, by encapsulating that state transforming function. The run method on line 13 is the entry point for actually executing the computation. It takes an initial state, the starting point for the process, and passes it into the stored function. That function then runs and returns a tuple, the result of the computation and the final state after all the changes. The map method, as you should now be familiar with from the other monads we've looked at, is a standard mapping function that lets you transform the result of the computation, that is, the TValue, without touching the state. This map method returns a new state instance, just like you'd expect from a functional pipeline, but remember, this doesn't run anything yet. All we're doing here is composing a new computation by layering on your mapping function. Nothing is executed until you call run. What's happening is we capture the mapping function, the one you pass into map, and compose it with the existing computation. Then, when the whole thing is eventually run, the current function is executed with the current state, producing the original t-value and the new state. That t-value is passed into your mapping function, and the result becomes the new t-value in the output tuple. The state is passed through unchanged. Next up is the bind method, which you'll recognize as the defining operation of a monad. This allows you to chain multiple stateful computations together, where each step can depend on the result of the previous one, not just in terms of the value, but also the updated state. As with map, bind returns a new state instance, but this time the function you pass in, bindFn, returns another state. So instead of just transforming a value, you're producing an entirely new computation. One thing to note is the use of the run local variable. We're assigning _run to a local here because you can't directly use the _run field inside the lambda expression. The compiler doesn't allow it, so we capture it up front. Then, when this combined computation is eventually run, the current state is passed into the captured function. We get back a value and an intermediate state. That value is then passed into the bindFn function, which gives us a new state, and that state's _run function is immediately executed using the immediate state. The result of that becomes the final value and state that we return. Next up is the return method. This is how we lift a plain value into the state monad, so it can be used in a monadic computation chain. If we take a closer look, return takes a value of type TValue and wraps it in a state of TState TValue instance. What's happening under the hood is that we're building a function that takes the current state and returns a tuple made up of the value we passed in and the state itself unchanged. And that function is stored inside the monad, ready to be run later. So just to be clear, when you eventually call run, this function doesn't do anything fancy. It simply returns the value and passes the state through untouched. This is useful when you want to inject a value into the monadic flow without modifying the state. For example, as a starting point in a computation, or to return a result after using something like put or modify. Next, the get method. This gives us access to the current state at any point in the monadic pipeline. It returns a state of TState TState. In other words, when you eventually call run, it returns the current state both as the value of the computation and also as the next state in the chain. The actual function being stored here is really simple. It just takes a state and returns a tuple of that state as both the result and the new state. Now let's take a look at the put method. This method is used to replace the current state with a new one. It takes a TState for its value. This is the new state that you want to set and returns a state of TState and none. So it basically just updates the state but has no meaningful computation value. Internally, the function that's created still accepts the current state as input because that's how the monadic chains work. State is always passed along from one computation to the next, but put doesn't make use of that incoming state to build its result. Instead, it discards it and replaces it with the new state that you've provided. So to be precise, it doesn't ignore the input entirely. It receives the current state as expected, but doesn't use it to calculate the next state. The provided new state simply overwrites it. This is handy when you've computed a new state externally, say inside a bind, and now you want to inject that into the monad without returning a value or inspecting the previous state. The modify method is a convenient helper that lets you update the state by applying a function to it without needing to explicitly call get and put. Here's what it does. It first gets the current state using get, then it applies a modifier function to that state to create a new updated state. Finally, it puts the updated state back using put. Because it uses bind internally, this chaining happens cleanly and composably. But as a user, you just need to provide a function that describes how the state should change. This makes your code simpler and easier to read whenever you want to update state based on its current value. Okay, let's see the state monad in action. But before we dive into the demo code, we first need to take a quick look at the record I created to represent the state. Our shop state record models the state of a simple shop holding an inventory, a dictionary mapping item names to quantities, and a cash balance. It also provides convenient methods to update the inventory or cash, which returns a new immutable shop state instance with the changes applied. Next up is the code for the demo, starting with the sell item method, which we'll be calling multiple times. I decided to keep things simple and focused by using just a single method that we can chain rather than creating multiple methods. This helps keep the attention on how the state monad works rather than the specific operations. Of course, in a real-world example like a banking system, you might have methods like transfer, deposit and withdraw, all updating some account state. The pattern would be exactly the same. Now let's break down this sell item method. This method returns a state of shop state and a decimal value, meaning it describes a stateful computation that reads from and potentially updates a shop state while producing a decimal result, which in this case is the value of the sale. We start by using the static get method, which is a predefined method that gives us access to the current state, in this case our shop state. Since get itself returns a state monad, we use bind to work with the actual state inside it. Inside the lambda, we first perform a guard check. We make sure that the requested item exists in the inventory and that there's enough quantity to sell. If that check fails, we simply return 0 for the value and return it, and crucially, we don't update the state. That way the original state is preserved and we've made the failed sale explicit without any side effects. If the check passes, we calculate the new quantity in inventory by subtracting the amount sold. We also calculate the sale value and the new cash total by adding the sale amount to the current cash. We then create a new shop state with the updated inventory and cash using the helper methods with inventory and with cash. This gives us an immutable copy with the changes applied. Finally, we return a new state using put, which replaces the current state with the updated one. But we don't just stop there, we also want to return the sale value. So we chain on map to return the computed sale amount, discarding the result from put, which is none. So this method not only handles validation and business logic, it also clearly separates reading, updating and producing a result, all using the structure of the state monad. Now let's look at how we use this method. On line 14, we create the initial shop state. This contains our starting inventory, some apples, bananas and oranges, and an initial cash value of £100. This state will be passed to the run method later to kick off our workflow. Next we print out these starting values, just so we have a clear before picture. On line 20 we define a sales process which is a state monad representing our full sales workflow. It starts by calling sellitem to sell 2 apples at £1.50 each. Then using bind, we chain additional calls to sellitem selling bananas and oranges, and finally making an attempt to sell more apples than we actually have in stock. Now in this version of the workflow, notice that each bind uses an underscore to discard the previous value. That's because we're not interested in tracking individual sale values at this point. We're just focused on sequencing the operations. Also, nothing is executed yet. This is important. All we've done so far is build up a chain of deferred computations. No state has been read or changed. Then on line 25 we call run on the sales process, passing in the initial shop state. This triggers the actual execution. Each sell item call gets run in sequence, updating the state as needed. The result is a tuple, the value of the last sale operation and the final updated state of the shop. We print these out so we can compare the final shop state after all sales. To demonstrate how you might capture intermediate results, we run a second version of the workflow. This time we use the current state from the first run as our starting point. Here, rather than creating a separate variable for the workflow, we just build and immediately run it, capturing the result tuple directly. Notice that the bind calls in this version are nested lambdas. That allows us to hold on to each intermediate sale value, apple sales, banana sales, orange sales, and then add them all up in the final map call. The total is returned as the result of the computation, which we store in run sales. And finally, we print out the total sales from this second run and the updated shop state. Alright, let's run it and take a look at the results. Now I know this might still feel a bit abstract, but once you download the code and step through it mentally, following the flow of the state and values, things should start to click. Until then, you'll just have to trust me that everything is working as it should do. And I think with that, we are done for today. I hope you found something of value in this episode. As always, feel free to leave feedback, positive or critical, and I'll do my best to answer any questions you have. If you found the video or source code helpful, please consider liking and subscribing to help the channel to grow. Thanks for watching, and until next time, bye for now.